In this lecture, I'll talk about the Kodaira embedding theorem. So in the first part of the video, I'll talk about what's special about positive line bundles on projective manifolds. We'll see the fact that they exist. I'll state the Kodaira embedding theorem, and then I'll say a few words to finish up about the strategy of the proof, maybe expand on it in a further video. Okay, so let's jump right into it. So let's recall some things about projective space first. So n-dimensional projective space. Right. So all n+1 dimensional directions. Right. So vectors from Cn+1 on vanishing. And then on Cpn, I'm looking at the tautological line bundle. Right. So we know what that is. Quickly to recall, right? So it's the line bundle where the vectors are vectors associated to each direction on Cpn, right? So a pair V is in O -1, right? If V is an alpha times Z0, Zn, right? Alpha complex number. Okay, so there is a natural Hermitian structure on the tautological line bundle. So this has many names. Tautological line bundle. It's essentially you just restrict the Euclidean metric to this line bundle, right? So HVW, where VW, these are vectors in O inverse at the base point, let's say Z0, Zn. So HVW, it's nothing but the Euclidean scalar product, right? So this is Euclidean inner product, Hermitian inner. Okay, so we learned how to compute Chern curvature theta h in the previous video. So in the next few minutes, I'll tell you what the curvature of h is. So really the question is, so what is theta h? For the definition of this, see the previous video. So how do we compute that? Well, I need to take a trivialization of the tautological line bundle. So, and then the tautological line bundle thankfully can be trivialized over the canonical cover of projective space. So those are what? So the UJs, right? These are all the directions where you take one in the J direction and whatever you want the other directions. All right, so ZK is in C. Right, so as you know well, so the union of the UJs, right, so is Cpn. And then what's great is that on top of these UJs, there's going to be a natural trivialization of the tautological line bundle, right? Namely, these vectors, all right? Let's call them Vj, right? They are in O inverse on top of Uj, right? And they're also non-vanishing. So I can compute the Chern curvature in terms of them. So for those, I need to compute what Hj is. So Hj, right, is nothing but the length squared of the Vj. So in this case, that is going to be what? It's going to be right, so it's going to be, so this is the Euclidean inner product. So this is Z0 squared all the way to zj minus 1 squared plus 1 plus zj squared plus zn squared. So then theta h, right, restricted to the uj is nothing but, so see the previous video. So this was negative I del bar of log hj. So it's negative I del bar of log of this sum. And then hopefully you'll recognize something. Okay. So plus cheat a little bit and then I got room. So this is nothing but the Fubini's 2D metric. It's just that there's an annoying negative side, negative sign in front of it, but it's okay. So this is the Fubini 2D Killer metric of Cpn. So we're looking for a positive line bundle, and then what we got is the negative. But if you recall some facts about line bundles, well, you know how to make a positive sign out of this negative sign here, namely, right? So you take the dual line bundle, which by definition, we can call it O1, right? So sometimes this is called the so Serre's twisting bundle, or I think it's called hyperspace, the hypersurface bundle, okay, and maybe it has many other names as well. You can just think of it simply as the dual of the tautological bundle, and then you can take the dual Hermitian metric on it. And then, as you know, so recall, the curvature of H star is always equal to the negative of the curvature of H, which in this case is omega fs. So this could be a quick homework exercise for you, unless you're already familiar with it. Now, the good thing here is this is positive. So in particular, right, so O1 with the metric H star is a positive line bundle on Cpn. Okay, so now we get to projective Killer manifolds. So suppose X is embedded into Cpn. So such things by definition are called projective manifolds. Now, one thing that's quite obvious, right? So if let's call this embedding a J, so the pullback bundle, right? Right, is also positive line bundle. And then recall, this follows from the fact that we elaborated at the end of the previous video, right? So quite simply, right? So the curvature of the pullback metric is nothing but the curvature of the actual metric restricted to the small manifold, right? So if this is positive definite, then this is also positive definite. So in particular, you know that if X is a projective Killer manifold, so again, a Killer manifold that embeds into a copy of Cpn, then so there exists a positive line bundle L on X. Okay, so this we get for free, and then Kodaira's theorem says that actually you can reverse the arrow. So if there exists a positive line bundle on a projective Killer manifold, on a Killer manifold, then it's projective. So there exists a positive line bundle on X where X is, let's say, only known to be Killer, then X is actually a projective manifold. Okay, good. So one direction, as I said, follows from what I just shown to you. So I'll give a sort of a quick strategy of the proof, and then hopefully I can elaborate more in a subsequent video. Okay, so this direction is the easy direction. And for the reverse direction, right? So what we know, right, is we have a complex manifold with a positive line bundle on it. So LH, right, is a positive Hermitian line bundle, because I specified a metric already on X. Now, the first thing to notice is that LK, where by power we mean tensor power, so k-fold tensor power, with the corresponding Hermitian metric is also a positive Hermitian line bundle for all k natural numbers. Okay, and then how do you see this? Well, recall the definition of the curvature operator, right? So it was locally, it looked like negative I del del bar of log H alpha. Okay. All right, so what can you tell about the curvature of HK? Well, so locally, it's I del del bar log of H alpha to the power K. Okay, but obviously logarithm spits out the K, so it's negative K times I del del bar of log of H alpha. So this is nothing but K times theta H in a trivialization, but obviously this is true over all the trivializations. So you get this formula that curvature of H to the power K is K times curvature of H, which is positive definite, right? So in particular, what I said here holds true, that any tensor power with the corresponding Hermitian metric is also going to be positive. Okay, so the first thing that we will show is that, so for K high enough, so don't care how high, but for high enough K, it's possible, so there exists, so for all points of the manifold X, there exists a global section of L to the power K that is non-vanishing at X. So somehow there is some global generation kind of property here going on with some high power of L, right? So at all points, you can find a non-vanishing global section of your line bundle L to the K, right? And then somehow the fact that, so what's going on here, right, is that all these theta H are positive 1-1 forms. In the route that we will take, what will help us is that every time you take higher and higher Ks, this form here will become more and more positive, and then somehow this will be something that will be of great advantage for us. So we can do this. So then what you do is pick a basis of global section. So pick a basis S0 SL of the vector space of global section. So one thing that's also worth arguing, I'll spend some time in, this is a finite dimensional C vector space. So this is possible, right, where L will be the dimension over C. Okay. And then using such a basis, any basis, you can write up a map, let's call it phi k, where k is this index here, that's high enough, from x to Cp to the power L. So you can write down a map, and then you want to show that it's actually an embedding. So what will be the definition of phi kx, right? So x is a point on the manifold. So you just take the value of S0 at x, the value of S1 at x, all the way down to the value of SL at x. Okay, so there is something to verify here, right? So first of all, how do you interpret this? So certainly, if you can think of these things here, all these entries here as numbers, right? So you know that one of them has to be non-vanishing because of this property here. So then this will be in CPL. But the question is, how do you interpret these entries here as in numbers? Well, what you do is pick a trivialization L near X. Okay, and but so then you look at each of these global sections in that specific trivialization. But then there is the concern that different trivialization will give you different entries. Well, then the projectivity helps you out. Well, the difference will be always a conformal factor, right? And then what will help you out is this square bracket here, right? So the square bracket will help you out in making sure that different trivializations will always give you the same direction in CPL. So perhaps a few minutes worth thinking about this on the side. So go ahead, stop the video, think about this a little bit. Okay, so then at least we have a map, and then you want to show that this map is an embedding. So this will be also shown in stages. So what we will show is that perhaps by increasing the k further, the phi k is injective. Right? So then now you have an injective map of X into CPL. Unfortunately, this not quite an embedding still. So what the very last step is to show that perhaps even increasing the k further, all the Jacobians of the phi k at every x are non-vanishing. It's x on your manifold. Okay, so injective plus all the Jacobians are non-vanishing. This indeed shows that phi k is an embedding. Okay, so this is the strategy of the proof. And then again, so there's three things to argue. The first one is this one. For k high enough, given a positive line bundle, you can find non-vanishing global sections near all the points of your manifolds by taking higher and higher powers. Next, we need to show, so with that property, we'll be able to define this map. Then what we will show is that for high enough k, the phi k is actually injective. And then for high enough k, all the Jacobians at every point will be non-vanishing. So what we will see is that it's actually possible to replace the injectivity and the non-vanishingness of the Jacobians also in terms of properties of these sections. And then again, the positivity of the line bundle will sort of do all the magic. All right, so that's all I had for today. I'm hoping I can do maybe another video on further details on the proof. So see you later.